So this is in your notes, so like you said, f of x is continuous at x equals c if and only if three things happen. The limit of f of x as x approach c exists. F at c exists. And those two things are equal to each other. Now, sometimes it's just so straightforward, it's scary. I mean, if I said something like, is f of x equal to x squared minus 2x plus 3 continuous at x equals, let's do something quick, 0. Well, I'm going to check the limit of my function as I approach that number. So my function is x squared minus 2x plus 3. Now, isn't that a polynomial? So what do you know that you can do with a polynomial when you got a limit? You can just do what with it? Plug it in and go. So I'm going to have 0 squared minus 2 times 0 plus 3, which is what? 3. Now I've got to do f at 0. Now what does f at 0 mean? It means take 0 and plug it into your original what? Function. That looks awful familiar. What do I get? 3. And sure enough, that limit as x approaches 0 is exactly the same number as f at 0. 3 equals 3. That's my argument. It's tight, it's precise, nobody has, there's nothing wrong with it. Now, you told me that this was a polynomial. So does it make sense to you that a polynomial is going to be continuous what? Everywhere. All the time. Because how do you get the limit on a polynomial? Don't you just take the number and do what? Plug it in. How do you get f at the number? You take the number and what? Plug it in. So when it's a polynomial, you're like home free. You know it's continuous. And you can show it for a particular one. All right. In your book, I'm pretty sure at some point they're going to tell you that they're continuous everywhere. All right. Now, sometimes it's not as straightforward. Sometimes it'll be something like this. Is f of x equal to x squared minus x minus 6 continuous at x equals 3? Let's do it this way. Let's put it over x minus 3. Is f of x equal to x squared minus x minus 6 over x minus 3 continuous at 3? Why not? Now, I'm not even going to check the limit. Now, we'll check the limit in a second. It doesn't matter about the limit because I immediately notice what? I notice that f at 3 what? Doesn't exist. Game over. I can go check the limit, but that's kind of a waste of my time. It doesn't matter if the limit exists or not. So you're going to say, so over here, you need to say, now, by the way, if you see 3 dots in a triangle in math, that means therefore. Like I told you, we like the notation. We don't like to write a lot of words. All right. So I can say over here, therefore, f of x is continuous at x equals 3. So over here, I could say, therefore, f of x is not continuous at x equals 3. Because I just told you, every 3 what? Doesn't exist. Question.
On the test, do you want us to show all of the parts, or if we can figure out that it's like not continuous, just show why it's not?
You have to either show all 3 parts checked so it's continuous, or you got to show me something that doesn't check. So if I immediately see something that, if I immediately see the limit's not going to exist, I'm going to go do it first. If I immediately see that f at the number doesn't exist, I'm going to go do it first. Now, sometimes, excuse me, it's a little more fun because you have a piecewise function. Like some of the ones on the homework, I think. So what if I told you, here's what f of x is. It's 2x squared if x is less than 0, and it's 3x if x is greater than or equal to 0. And I ask you, is f of x continuous at 0? Is it continuous at x equals 0? Oh no. Now, I think, okay, well, I need to check the limit of f of x as x approaches what? 0. Now, what should I plug in for f of x?
3.
Should I plug in 3x? 2x squared? What do I plug in? I got a problem. I know that I'm getting close to 0, which means I'm never what? I'm never there. Am I on the left side or the right side? Oh no, I got to come from both, right? So what I'm going to have to do is I'm going to have to do a longer argument for this one. Because if I'm on the left side of 0, what's my function? Is it 2x squared or 3x if I'm on the left side of 0? 2x squared, because if you're on the left side of 0, you're what? Less than 0. If you're on the right side of 0, now I'm what? Bigger than 0. So now my function is not part of a parabola, it's part of a line. So I'm going to have to kind of do it like this. The limit, if I approach 0 from the left, what do we agree my function was? Is it 3x or 2x squared? 2x squared. Now, isn't that a little polynomial? So can I take that 0 and just plug it in? Okay. So I get 2 times 0 squared, which is 0. Now, if, however, I'm getting close to 0 from the right side, my function is no longer 2x squared. Now what's my function? 3x. Now again, isn't that a polynomial? So can I take 0 and plug it in for my x? And I get what? 0. Now we talked about this the very first time we ever started limits. When there's no superscript, I've got to come from the left side and from the right side, and I've got to get the same value. Did I do that? So what's the answer to this? The answer to this is what? 0. Now, what have I still not checked yet? I've got to check f at what? 0. Now, do I plug it in the top and the bottom like I did here? Do I need to plug it into the 2x squared and the 3x? No, why? What does this mean? This means x is exactly what? When x is exactly 0, what's your function? 3x. 3x. It's when it's bigger than 0 or when it's exactly 0. So the only one I got to plug it into is the 3x. And 3 times 0 is 0. Now I'm going to run over here if I'm running out of room. So I'm still not finished. What if I still not shown somebody? That those two things are what? The same. Because I got 0 equal to 0. So therefore, f of x is continuous at x equals 0. Now, if you were to draw that graph, does everybody understand that you'd have part of a parabola over here, and then over here, you would have part of a line. But they're connected. So I can draw this graph without picking my pencil up. Discontinuous. Now, what if instead of it being 3x, what if it had been 3x plus 1?
Uh-oh, wait a minute.
I'd be in trouble. Because now, this is still going to be 2x squared. Everybody with me? But this one isn't 3x. What's this one now? 3x what? Plus 1. But it's polynomial. So when I substitute in, I get 3 times 0 plus 1, which is what? 1. So what does that mean about this limit? It doesn't exist. So is there any reason to go any further? No, now still, I would have had to plug into 3x plus 1 here. Why would I keep going? I mean, if something's already false, the game is over. Is everybody with me? So then I would stop and say, therefore, f of x is what? Not continuous. Because when I look at this graph, I've got this, but suddenly, I mean, it's an open hole right there. Suddenly, that's my picture. It's not continuous. The limit doesn't exist right there. It's discontinuous. So discontinuous just means not what? So if I've got a piecewise function, I've got to usually check the left side and the what? The right side. And I need them to match. Sometimes they do, sometimes what? They don't. Okay? And that's the way you're going to argue for me whether something is continuous or it's not. So does everybody feel okay then about doing me a proof for continuity? You have to check those 3 things until all 3 check or until one of them is false. As soon as one of them is false, the game is over. Okay? It's much easier to prove something false than true. Because to prove something false, I've only got to find one time it doesn't work. Okay, which reminds me, people sometimes on a true false test. I've had people like make up their own test. Like they will insert words. They will scratch words out. They will write me a note to the side. Sometimes this is true if it's blah, blah, blah. Sometimes it's false. I don't need any of that. True in math means always true. What does false in math mean? Not always true. False does not mean always false. In math, false simply means not always what? True. It may be true 9 million times, and one time it's not true, it's not true. That's why you broke a commandment. You broke 10 commandments. So sorry, you can't do it. So if you have to write me a note or insert a word or scratch a word out, what goes in the blank? False. Or
How can we prove things in truth, like in math, whereas like in science, like for like hypotheses and like theories, we can't like prove a hypothesis is true, prove it's not wrong. You know what I'm saying?
so you're saying why can you do it in math and why can you not do it in science? Is that your question?
I guess like definitively.
Definitively? Well, first of all, I do need you to understand. Everything is eventually based on an unknown. Like all of geometry is based on 3 words: point, line, and plane. And there's no definition of either of those words. So you build a whole mathematical system on something that you just take for granted. You know what I'm saying? But you do that every day. Christian or atheist, you start with something at the bottom that you take as truth. There is a God. There's no proof for that. There may be some evidence, you see what I'm saying? But you have to start with an unknown. If you're an atheist, you also start with an unknown, and your unknown is there is what? Not a God. I mean, everybody starts with an unknown. Well, in math, what happens is you have a couple of things that you start with that you assume are true. And then you have to build everything from that. So that's what I mean by anytime somebody tells me you can do this, I'm like, whoa, whoa, whoa. You got to back that truck up. Because you got to be able to prove to me using, if we have to eventually almost all go all the way down to the unknowns. Like you've got to convince me why 1 to the 0, why 5 to the 0 is 1, because that just doesn't sound right. Now, the lovely thing though is because of that, there's some solid, what we kind of think of as truths. I mean, mathematicians get a little, let's go with arrogant. Because we can definitively say that is what? True. Now, that's why one of my favorite quotes is Galileo. He's one of my favorite people ever to have lived. And he says that mathematics is the language with which God has written the universe. So, you know, what can I say? So while eggs are good for you one day and bad for you the next day, you know what I'm saying? While this causes cancer one day, it doesn't cause cancer. Now, the joke is this though. I remember going home when I was in grad school and telling my husband, did you know that 2 + 2 can equal like 7? And he just looked at me and he goes, I knew this would happen one day. Because I'm in a different number system. So I have to make qualifiers. In this number system, if A, B is 0, either A is 0 or what? But that's not true in modern algebra. That's not true in other number systems. So some truths are even relative to what system you're in. Same thing in geometry.
There's different numbers. Yeah.
Oh man, yeah. Euclidean geometry is not even real.
Oh, what?
And what I mean by that is this. You live on a globe, don't you? You live on a freaking sphere. You don't live on a flat surface.
No.
The ground you're walking on is part of a sphere. It's not straight. So there's spherical geometry, which means lines or circles. Now, that doesn't freak you out. Didn't you take geography as a kid? Didn't you have lines of longitude and lines of latitude? Those were circles, weren't they? You better hope the pilot knows spherical geometry, because he's going around a globe. You see what I'm saying? So there are other kind of geometries where when you add 3 angles in a triangle, it doesn't come out to be 180. I mean, it's so much. Okay, now, so much fun. Okay. Now, you see, you never know. Your world is nothing's the same anymore.
Okay. Geometry. My bad, guys. Didn't mean to.
All right. Let's talk about this graph because your author likes it a lot. So it shows up. And I found that most people haven't seen it in high school. I don't know why. Okay, so it's like a double bracket on both sides. The name of it is called the greatest integer function. So what that means is the value of this is the closest integer to x that is less than or equal to x. Now, what I need you to think of is the price is right. So is the closest one without going what? Over. So if I need to graph it, what if I plugged in 0? Now, think about a number line. So I need the closest integer to 0 that's less than or equal to 0. Do you understand that would be 0? Because it can be less than or what? Equal to. Now, so 0, 0. Now, what's going to happen if I go over like 2/10? So now I'm like right here. So what's the closest integer to right there without being bigger, without going past there? What's that going to be? 0. What if I had 6/10? 0. Everybody with me? What if I had 9/10? 0. But what if I finally get to 1? What's going to happen when I get to 1? What's the closest integer to 1 that's less than or equal to 1? 1. Now it jumps up here. What's going to happen if I'm at 1.2? Still going to be 1, isn't it? What if I'm at 1.5? Still going to be what? 1. If I'm at 1.9, it's still going to be what? 1. Now, as soon as I get to 2, though, what's going to happen? It's going to jump up to what? To 2. When's it going to jump up again? You understand? A 2.1, any of those. When it gets to 3, it's going to jump up to 3. Is everybody with me? Now, what's going to happen on the negative side? What if I've got a negative 0.1? So now I'm like right there. What's the closest integer to negative 1/10 without being bigger than 1/10? Negative 1. So it's not just the first part. Everybody with me? It's not the unit. All right, so if I'm here, I'm like down here. Now, what they call this, they call it a stair-step function. So what would the answer to this be? What's the limit on that greatest integer function as you get close to 1? Doesn't what? It doesn't exist. Stair-step functions, their limits don't exist at the jumps. Is everybody with me? And sometimes in your author will put like an x plus 1 in there or a 2x in there. So you're going to make a table and look at it. But you're not going to have limits at those jumps. And in the real world, you have a lot of greatest integer functions. You know, the tax is this much if you buy 5. If you buy 10, more than 5, it becomes this. If you buy less, it jumps. The price changes as you buy more. So in the real world, you have things that are stair-step functions. So he kind of wants you to see. Let's see. What else he talks about? We've already talked about left-hand limits and right-hand limits. He talks about on page 99 some properties of continuity. He says if you know a function is continuous, any scalar multiple will be continuous. So you can multiply a function by a constant, and if it was continuous, it's still going to be continuous. When you add 2 continuous functions, that new function is continuous. When you multiply 2 continuous functions, that new is continuous. So it gives you those properties of continuity up there. Now, there's a theorem on page 101, and the reason he gives it to you, he uses it in a proof later. It's what's called an existence theorem. An existence theorem just tells you that something is there. Now, it's useful for some things. It used to be even more useful 1,000 years ago before you had a graphic calculator. So look what it says. Here's what your intermediate value theorem says. I just want to show it to you. It says if f is continuous on the closed interval AB, and f of A does not equal f of B, and k is any number between f of A and f of B, then there's at least one number C in the interval AB such that f of C equals k. Now, what does that say in English? Here's what it says. And this is what it really was this is one thing it used to be really useful for. if you know for sure that your function is continuous between like A and B. So if this A down here is like a negative, you know, suppose that's the point like -1/2, comma -12. Suppose over here this B is the point like 5,8/3. I don't know. So do you understand that from -1/2 to 5, that this thing is continuous? And when it's at -1/2, the y value is a -12. And when it's at 5, the y value is what? 8/3. Then there's got to be some number between -1/2 and 5 where the y value is every number between -12 and what? 8/3. So there's got to be somewhere that the y value is a -1. Somewhere on this graph, that thing is exactly -1 down here. And that number's got to be between -1/2 and 5 that will get you that. Is everybody with me? Now, why was that super useful? Because a lot of times you have to find roots of things. You have to find zeros. Well, you got a tracer key on the grapher that'll get you an approximation. Now, sometimes zeros are easy to see. Like if I said something like x² minus x minus 6, when does that thing equal 0? You factor it. And you'd say x minus 3 and x plus 2 is 0. So either x is 3 or x is a what? -2. So you know that when x is 3, the y is going to be 0. So 3 comma 0 is on this parabola. -2 comma 0 is what? On that parabola. But if I gave you x to the 6 minus 4x cubed plus the square root of 17x minus 11 is 0, now you're going to balk. Because factoring that's not going to be fun. So what would happen is you would find some number that would give you a negative answer. And then some number that would give you a positive answer. And you know there had to be a 0 between this one and what? And that one. And so what you would do is you would just keep getting them closer and closer together until you found a pretty good approximation for where that was. I call it number crunching. It wasn't fun. It wasn't hard, it was just tedious. But now, do you understand? If this function wasn't continuous, there'd be no guarantee. This thing might stop here and then jump up here. Is everybody with me? So if it's not continuous, there's no guarantee that there's going to be a number that will give me a 0. That's only true if it's what? Continuous. So this is the silly example that I always tell people that they still remember. Before I had my first child, it seemed to be the consensus of the world that I was too thin, too skinny. I didn't agree. But hey, after I was 8 months pregnant, we could all agree that I was too fat. So here is another reason I love mathematics. Weight is a continuous function. So here's what I can mathematically prove. If there was a moment in time when I was too skinny, and there was another moment in time when I was too fat, then because weight's a continuous function, I can mathematically prove there must have been a moment in time when I was perfect. Because you can't go from too skinny to too fat without going through freaking functions. Now, the problem is an existence theorem. It doesn't tell me when that happened, it tells me what?
It happened.
It happened. So I can mathematically prove it. So that's what this theorem is. It's an existence theorem. It can't tell you what that is. It just tells you that it's what? It's there. Because you don't want to go hunting for something if it's not there.
Or isn't that, I can't remember what it's called, but it's talking about like the acceleration we learned. I learned it last year in AP Cal, like you go from like 60 to 70. Like,
yeah, exactly. In other words, you're really glad high control does not know this. Because technically, they could clock you. at one point going 50, say the speed limit 70, if there were two apart and you're going 70 here, and then the next time the cop down here sees you're going 70, now does that mean that you were going 70 the whole time? What? Not necessarily. And if the average speed was more than 70, you understand like I'm saying? If it took you a certain amount of time to get from point A to point B, if the average is more than 70, he could mathematically prove there must have been a moment in time when you were going more than what? 70. So we're not teaching any kind of hyperdrive calculus. And it was done in court. It's a mathematical proof. So we're not telling. Okay. No, we're not teaching calculus in the hyperdrive. Now, so that kind of ends up that section. So the intermittent value theorem is great. It's good. It's useful. It's used in a lot of proofs. It's used to find zeros if you need them, but we don't need them right now. They use it for something later. So that's why they kind of introduced it. Now, as far as this section goes, what you're going to have to do in this section is you are going to have to prove whether something is or it's not continuous based on the definition. So does everybody feel okay about that first? Now, when is your test? Monday. Your test is Monday, so I want to talk about it for a minute. Okay? Now, you are welcome within reason, like I said, to take as long as you want to take on the test. As long as you start right at 1:30. Now, there's a class that comes in here, so I'd have to move you. So I'd move you upstairs to the conference room or something. So I don't want you getting a big ripping hurry. All right? Does everybody understand what's on the test? Does anybody have a question or a clarification about anything on the test? And we still got like, what, 18 minutes, so we're not going to break. Okay, so I'm not asking questions in a minute. Okay?
So none of the continuity stuff's on there.
No, continuity's not on there. The last thing that's on there are the limit things.
Are you going to specify on the test which parts we have to justify or prove? Or
Yes, it'll say up there like you must justify your answer. And you can always ask me clarification questions. Like I'm not going to tell you how to work something, I'm not going to tell you something's right or wrong, but you're welcome to come up here and go, is this simplified enough? You know what I'm saying? Because that's kind of a judgment call for some people. Like, is this good enough? You know, you want me to go any further? But yeah, I think it's pretty explicit.
You're cool with unrationalized denominators?
Yes.
Okay.
Well,
You know how many questions the test is going to be?
how many questions? I haven't made it out yet. It's usually around 3 pages. And all the problems don't count the same. You know, a true false ain't gonna count as much as you do in a limit or something. You know what I'm saying? Like, it's just not. So they're varied amounts. Do make sure, like we talked about last time, that you go back and learn those definitions. Okay, because it's just defined.
Do they have to be word for word like you gave us in class?
They don't have to be word for word, but the only thing I would say is, this kind of goes back to what we laughingly talk about. You got to be careful changing the wording. Because, for instance, if you say a group of numbers, there's a whole mathematical definition for the word group that you just came out of your mouth. You don't know it, but I do. So it's not a problem with changing the definition as long as it means the same thing, but sometimes you just got to be careful with that. Okay?
Solving a limit using the proof that's on the x minus l.
Yeah, in other words, that might be on there. That's right. It would be a simple linear one like you had.
We are allowed to use our calculator.
Yes, you are allowed to. Now, we'll tell you this. I reserve the right to take your calculator and wipe them out. So just make sure if you've got programs in there, you might want to back them up somewhere. Because if anything looks the least bit suspicious, I'm just going to pick it up and wipe the memory out and do it. Okay. And I'm not saying you're cheating when I do that. I'm just saying this makes me feel better. I'm wiping your memory out. So, you know, I've done that before, people are not. I'm just saying I've reserved the right to do that. So I'm just saying if you've got programs on there, you want to back them up somewhere.
Could you put it on Moodle, like more like practice problems?
Sure, I'd be happy to do that.
Okay.
Now, I do not pull problems from homework to put on tests. But if you're doing well on your homework, you will do well on the test. They are very similar in nature. So when I'm studying, what I always do is, the first thing I do is learn all the definitions. All right? So, I mean, anybody can memorize. So, that's get that done, get that out of the way. Then the next thing I would do is I would go make almost an outline of all the different questions that person could ask me, like topics. Like, I've got to be able to do like, trig, words, and an angle. She might give me the answer's this, what's the angle? It might be, I've got to solve a quadratic inequality, like on that review sheet. It might be, I've got to do the limit, and sometimes I have to rationalize, sometimes I have to factor, just all the different types. All right? I've got to be able to find domains of functions. What are my two trouble spots? If I can't just say it, I've got no hope of doing it. Okay? So I'm going to go through all the different types of problems. And I'm going to be able to say out loud what to do. So if she asks me to find the domain of a function, if it's a rational function, I'm going to take the denominator and I'm going to set it equal to 0, and my answer is all real numbers but those answers. If she gives me a root, then I'm going to take what's under the root and set it greater than or equal to 0, and when I solve that, that is my answer. You know what I'm saying? Like, I can say out loud how I work the problems. When it's limit, I'm going to try to take the numbers, plug it in. If that works, I'm done. If that doesn't work, I got some tricks. I could factor it. I could, I'm doing all of it. I'm just making in my head what to do. Then I'm going to go work one of every kind of those. Now, if I work one and I get it right, that tells me I could say it and I could do it. If I don't get it right, now I've got to go work like 5 or 6. Because here's what happens every time on a test for me. Somebody won't do well, and here's what I was going to tell you. In calculus, if you make a D or an F, you've got to meet with me to stay in the class. Okay? And the reason for that is it didn't go well, so I need to know that you have figured out why it didn't go well. So it's not to punish or to chastise you, it's to help you problem solve. Because nobody wants to make a D or F in a class. Okay? So I'm going to ask you some questions, and the first thing I'm going to ask you is, did you do your homework? And sometimes the student honestly looks at me and goes, no, ma'am, I didn't. And I go, well, that's an easy fix. Start doing your homework, problem solved. Now, sometimes they'll say, most of it, that means, no, ma'am, I did not do my homework. Okay, so again, that's easy to fix. But sometimes I'll say, did you do your homework? And they will say, yes, ma'am, I did my homework. And I'll say, did you do all of it? Yes, ma'am, I did all of it. Well, the next question I ask them is this. How often, when you check the back of the book, were you getting the answer right the first time? And they'll go, well, I don't think back when you were doing your homework and you flip to the back after working number 17 and you check the answer, how often were you getting them right? Most of the time, give me a percentage. 50%, 60%, they'll go, I was getting it right, I don't know, 70% of the time. And I'm like, well, look at your grade, you made a 64. But it always matches. Because when you're looking at the back of the book on your homework and the answer's not right, you're brilliant and you're a very good student. So you know, oh my gosh, I made a mistake. So you go back through your work and you find your mistake. But the problem is the test doesn't have a back of the book. So when you take your test, it's like working your homework the first time. So you have to work enough problems so that you're getting them right the very first time, at least 80% of the time. If you're not getting them right the first time you check the back, 80% of the time, you're not working enough problems. Well, you're an adult. I'm not going to make everybody work 23 problems on that section because you had to work 23 problems on that section. Everybody has to work 23 problems on some section. So there are plenty of odd problems I don't assign. So you have to go keep working problems until you're getting them right 80 to 90% of the time the first time you check the back. Because when you take the test, you're going to be nervous. So it's going to drop a little bit anyway. Then sometimes they'll say, I was getting it right 90% of the time. And I'll say, well, did you study enough? Well, how do you define enough? It might be 3 hours for one person and 13 hours for somebody else. Because a lot of that depends on your background. If you've got a real strong background in algebra and trig, then you don't have to study it. You did your study in high school. But if your background's a little weak, now it's time to pay that bill. Now you've got to do more studying because you didn't study in high school. So I can't tell you how much enough is. That's a different amount for everybody. And sometimes you know you didn't study enough. Now sometimes there's a valid reason and sometimes there's an invalid reason. It doesn't really matter. I mean, it may be that you felt bad, that you didn't feel good, you were sick. It may be that your dad was having surgery and you were majorly distracted. It may be that you had 5 tests and you just couldn't get it all together. Or it may be you were lazy. It doesn't matter why. It's just if you didn't study enough, the next time you need to study more. So, one of the definitions of insanity is doing the same thing and expecting a different result. The world does not, never will, never has, it does not adjust to people. People have to adjust to it. So, just doing the same thing over and over, like I'll watch a student, they'll do the same thing like over and over, and I'm just like, oh baby, don't do that. It didn't work last time, not gonna work this time. So if you're studying a certain way and the results aren't good for you, you need to change the way you study. If working 9 million problems doesn't make your grade any better, then quit working 9 million problems. Try something else. And I will tell you that in math, normally what happens is, the best thing to do is to study smaller times more frequently. Because then the night before, like Sunday night, you should be like looking this over for 30 minutes and going to bed. You should have done your major studying like starting the night. Not cramming. Cramming does not work in math. Not once you get to a higher level, it just doesn't. Okay? So is everybody clear about what's on your test? I need a clean sheet of paper for me. Take this pop test, you put it, fold it, name on the outside like usual, you may go. What's your homework going to be? Study for your test.